What if the biggest barrier to the quantum revolution wasn't a law of physics, but an engineering hurdle we have finally cleared? Imagine a world where the fragile nature of quantum states no longer holds back our most powerful computers, allowing them to solve problems that today seem impossible. Welcome to a pivotal moment in the history of technology. Today, we are diving deep into the latest breakthroughs that are transforming quantum computing from a theoretical dream into a practical reality. We will explore how new hardware architectures are finally scaling up without losing their power, why a specific type of error correction is changing the rules of the game, and how these advances promise to revolutionize fields ranging from medicine to artificial intelligence. Stay until the end because the specific metrics we uncover today prove that the era of reliable, large-scale quantum computing has officially begun. For years, the promise of quantum computing has been shadowed by a single, persistent problem: noise. Quantum bits, or qubits, are incredibly sensitive to their environment, and even the slightest disturbance can cause them to lose the information they carry. This fragility meant that as scientists tried to build larger systems with more qubits, the errors would accumulate, rendering the computer useless for complex tasks. The field was stuck in a cycle of proving quantum supremacy in small, isolated experiments while struggling to engineer systems that could remain stable at the scale required for real-world applications. This bottleneck threatened to keep quantum computers as sophisticated laboratory curiosities, rather than the transformative tools we hoped they would be. However, recent research has revealed a decisive shift. Scientists and engineers have successfully demonstrated that we can now scale quantum hardware to hundreds of qubits, while maintaining the coherence necessary for computation. Google's transition to 67 and 70 qubit architectures stands as a testament to this progress, proving that size does not necessarily compromise stability. Even more striking is the performance of the new Willow processor, which has achieved a logical error rate of just 143%. To put this in perspective, imagine trying to transcribe a massive library of books by hand. Previously, one mistake in every 100 pages would ruin the entire collection. Now, with this new level of precision, the error rate is so low that the system can correct itself faster than mistakes occur, achieving a break-even factor that makes large-scale operation not just possible, but efficient. This leap forward is driven by a breakthrough in how we understand and correct errors. Traditional methods often assumed that noise behaves in a predictable, memoryless way, but researchers have now harnessed continuous-time quantum error correction to exploit non-Markovian dynamics. In simpler terms, instead of treating errors as random, isolated events, this new approach understands that past events influence future outcomes, much like how the ripples from a stone thrown into a pond interact with subsequent waves. By accounting for these complex, time-dependent relationships, scientists have achieved quadratic improvements in fidelity. This advancement is pushing quantum sensors toward the Heisenberg limit, the ultimate boundary of measurement precision, promising a new generation of medical imaging tools capable of detecting diseases at their earliest stages. The implications of these findings extend far beyond the laboratory. We are witnessing the dawn of the early fault-tolerant era, where quantum computers can reliably tackle optimization problems and simulations that are completely out of reach for classical machines. For the biomedical field, this means revolutionized diagnostics and more precise interventions within the next decade. In engineering and artificial intelligence, the standardization of frameworks like Merlin is bridging the gap between noisy prototypes and robust, deployable systems. The primary bottleneck has shifted. We are no fighting against the fundamental limits of physics, but rather refining the engineering scalability that will allow these machines to integrate seamlessly into our daily lives. In summary, the convergence of solid theoretical foundations with experimental breakthroughs has validated the path toward large-scale, fault-tolerant quantum computing. The transition from fragile prototypes to robust systems containing hundreds of logical qubits confirms that the technology is ready for the next stage of growth. As we stand on the brink of this new era, the potential for solving humanity's most complex challenges has never been brighter. Like, subscribe, and comment your thoughts on how you think fault-tolerant quantum computing will impact your industry first. Next time, We will explore the specific applications of these sensors in early disease detection, so don it away.